I greatly appreciate this opportunity given to me by the organizers, Professor Panchal and Professor Wang. And it's a great pleasure to share the forum with Mark, whose work I've followed since the beginning in this area. So I think the core message is going to be the same as Mark said, that this is a highly interdisciplinary field where mechanical engineers and computer scientists need to work together. But here, the security is not just the responsibility of computer scientists, and that's what I'm going to present today about. So mechanical engineers have a role to play, and we need to do some new things because of this whole additive manufacturing and how this technique works. And that's what is going to be the core of my message here. I'm affiliated with the Center for Cybersecurity, so there's a large team of interdisciplinary researchers in the center. But I'm a material scientist. I'm in mechanical engineering department here at NYU. So since this is an interdisciplinary field, I wanted to thank many of my colleagues and collaborators who collaborated on this research, ranging from people at NYU in different departments to many installations of Army and Navy and other universities, even international collaborations. And it's just not a field where one person can make a huge difference by himself or herself. This is where we do need collaborations. I wanted to thank National Science Foundation for funding much of this work through several grants we have from CMMI, from CPS, from Secure and Trustworthy Computing, and also from National Academies and Secure America Institute for security work. So I do have a few introduction slides, but they are not intended to give you any background on additive manufacturing. These slides are intended to set the stage for intellectual property that we are planning to protect and the systems that we have been using for years, but now we need a new set of eyes to look at these systems, just to gain perspective on how these softwares and hardwares are working and what outputs they are providing us. And we have a set of these traditional manufacturing methods, subtractive and formative manufacturing methods that we have been using, CNC machining and all kinds of things that are very common. It has taken hundreds of years to develop many of these methods, especially casting and forging. And we have a lot of control over the microstructure and mechanical properties and type of things that we create. So what exactly is different in additive manufacturing, why there is so much of enthusiasm about this technique is important to understand. And that's what also brings the many of the threats that Mark was trying to outline. So these techniques have been around for quite some time. We have perfected them to create large production volumes at low cost. And that's really the benefit out of many of these methods. But the limitation on the side is that we cannot create unique customized products, one of a kind at low cost. You always need to create tooling or molds and dies, which is additional cost, and it takes a lot of time to develop those molds, dies, and tools. If you have to create only one or a small number of parts, for example, for biomedical or space applications. And this is where additive manufacturing found its niche area and made a huge impact very quickly. The other thing that sometimes is missed in discussion is the requirement for trained workforce. So there's going to be a transition of the workforce from traditional to these modern manufacturing methods. But we have to understand that the role of the workforce is not the same as in traditional manufacturing, because a foundryman with accumulated experience had a lot of knowledge that you could rely on this person to deliver certain things. But now one person is operating from their own desktop, the entire process chain, starting from design to even 3D printing the part. And the printer operator is nothing more than really an operator these days. You don't require sophisticated skills or accumulated experience over a lot of years to operate many of these 3D printers. So that discussion should also be at the center. The difference here in this method is really that we create a CAD model, and then this CAD model is sliced into two-dimensional slices. And these slices are built on flat surfaces or the build plates. And you can design how this tool path is going to create the part. So it could be a powder bed method using a laser source or electron beam, or it could be an extruder that is extruding the material out. But the goal is to fill the space in 3 dimension and create the part. And now you can imagine that when you are slicing this 3D model into 2D slices, and then further you are slicing it into one-dimensional toolpath, there's going to be some loss of information in each of these steps. And so this is more or less a reverse process compared to what we used to do for CT scan, that you had 2D slices coming out from CT scan, and then we would stitch them together to create 3-dimensional shapes. But now we are going in the reverse direction. So there the problem was the artifacts that would come in imaging and other kinds of things, the missed sectors and all that. But here now, if you have features which are really small, they can be lost between these slices if everything is not done properly. So we started looking at this figure. It's very simple, but it's extremely illustrative. So I could design things in my CAD model, and if you don't slice it properly, those things, those features can either stay or they can be completely disappeared after your slicing step. So that's one starting point for us to start thinking that, information can be hidden in plain sight, and it may or may not survive at the end of the process. Can we use it as the security method that is tied to the design process? So in one sentence, if I have to give you my motivation, the motivation is that can design be a can security be a design constraint, just like the product performance metric. So you look for certain strength, you look for modulus, you look for failure modes when you design certain products. But same way, can you design also for security? So that's the challenge that we start with. Now, coming back to the intellectual property part, that we are always thinking about this intellectual properties protection. So why is it much more important in case of additive manufacturing? It's important for additive manufacturing more because we are creating these unique designs, sometimes one of a kind, sometimes a very small production run, but extremely high value parts. And there are examples given here that, I collected them from different sources. Most of these sources are here. Heat exchangers or fluid channels, complex geometries that you can spend a lot of time doing FEA or CFD and eventually come up with this geometry with internal designs. Unless you can manufacture it, then there's no point in creating the design like this. So since everybody here is mechanical engineer, a simple question is that suppose you have to make this design into two parts by traditional methods or machining or something. How many parts do you actually end up with? So if you cut something in two parts, you need to have gaskets or seals. You need to have number of nuts and bolts and stuff. So two parts is not really two parts. The two parts actually balloons to like 8, 10, or 20 parts very quickly. And that's what the reality we are looking at. And then you have problem of leakage. You have problem of seals going bad over a period of time, needing maintenance and replacement. So all those things can just go out of the door pretty quickly now if the part is made in a single piece. So the philosophy is not here that everything in the whole world is going to be 3D printed, but these are the designs where you do see distinct advantage of using additive manufacturing. And that's why industry is adopting it. So if you talk to Boeing and Airbus or car companies, you see hundreds and hundreds of examples of these parts. The other very illustrative example is right here. This is a bracket, which is current generation is the first part. And then additive, the topology optimization methods are used, and the final geometry looks something like this. Significant reduction in weight. In many cases, I've seen examples from Airbus where 90% weight was reduced compared to the existing designs. The size is also reduced, and this size and weight are now available for you to use in other systems or in payloads. So that's why the whole system design is triggered by some of the redesign of these simple parts. And this is why I think there's a lot of excitement going around there. And then there are these examples of medical implants like this one, a mandibular implant, which is patient specific. A lot of time these doctors were making decisions on the go in the operation theater. But now they can rely on CT scan, they can practice complex surgeries, and they can create these parts preemptively from the patient's own anatomy and then have a better intervention in those cases. I'm sure everybody has seen this GE LEAP jet engine nozzle. Another example where more than 20 parts were eliminated by 3D printing this one nozzle. So inventory is reduced, the number of failure cases are reduced, and there's a in general advantage of using parts like this. So moving forward to that the industry is excited about it, which is known from many of these trends. Uh, I'm sorry. Okay. And when reports like this come out, which say that the impact can touch $550 billion in 2025, I think this is more at the system design level that few of these parts are replaced with additive manufactured geometries. And now you have the whole system redesign possibility coming up, giving you a very different looking product or a system. But there's no doubt that 3D printing is really one of the fastest growing sectors in the manufacturing area. Growth rate has been around 20%. But anything that grows that fast and it's used in such critical applications, there's bound to be security implications there. So just an overview of what we are doing in 3D printing. We spend a lot of time developing these CAD models, and there's always this back and forth between CAD and finite element analysis to come up with final design these days. It's more or less standard practice. But once the design is finalized, in that case, the files are saved in a generic format called STL. And then these files are sliced. These are two-dimensional slices. And eventually a toolpath is created, which contains the information about how this extruder or the laser head should move on the build plate, along with all the printer specific information such as the temperature and the laser spot size and the speed at which it travels and all those parameters. Finally, this G code is what this 3D printer is going to use and print the part according to those instructions. Every printed part will go through certain qualification stages. It could be non-destructive evaluation or the destructive evaluation. So in cyber physical system like this, when we have discussion with our computer science colleagues, and we have seen many examples in my lab also, there can be attacks where system is severely compromised. But if that compromise does not translate into the product quality deterioration, then the production house is not going to care about that. And we have seen that in numerous cases where attacks were proposed, within our team in brainstorming, but then the product quality was not compromised at the end. And one example I'll give you is that, we had a extrusion of a composite wire for 3D printing using FDM printer that was going on in the lab. And we could compromise the process in such a way that there was severe porosity in that filament that was extruded. So now when we use that compromised filament in 3D printer, we realize that the printer is melting that wire again and extruding it again. So the final part actually did not have that porosity. So although that attack was important, it caused a compromise of the raw material, but that attack did not survive in the final printing of that part. So should we be worried about that kind of attack or not? And Mark brought up an excellent point that a huge number of these production houses are small and medium SME sectors. They don't have resources for cybersecurity. They are working for somebody else for production. And as long as they are producing parts that pass the inspection, those kinds of attacks are not going to be on their radar. But we still don't know the long-term consequences of something like that, and protection is always better in these cases. So what really is happening here in this case is we are also thinking a lot of times that these systems are secure, especially the aerospace systems and defense systems, which are the first adopters of many of these additive manufacturing systems. But then there are all these reports here, and these reports are putting a lot of pressure on the aerospace and defense sector itself, that these reports are about 10 years old in many cases, and these investigations don't happen often. $2 billion worth of unapproved parts were sitting with the distributors or airlines or repair stations at the stage where they were waiting for deployment on the aircraft. So now, if that is the condition in aircraft sector, then you can imagine that having all this pipeline of production being online, the counterfeiting problem can be much easier. We have 3D scanners available. A lot of people have CAD skills available. Softwares are also available more easily these days. And if there is enough motivation, people can hack and they can steal designs or recreate designs. And this problem is only going to grow. But that's not enough. It was also found that a number of defense systems, including the missile defense system, was found to have these unauthorized parts. Many of the military aircraft and helicopters were supposed to were found with these counterfeit parts. So if these parts can make into these highly secured supply chains, then you can imagine that a risk to civilian systems is going to be even higher. For the consumer products, is going to be much higher, and then we have to be careful about it. When looking at this picture now, the CAD softwares are collaborative, they are online, people are working together. Finite element analysis, again, a software operation. STL conversion, another software operation. Slicing, another software operation. Toolpath, another software operation. And then you come to printer where you have firmware, you have hardware, and softwares working together. So there are numerous attack vectors that you can imagine here. And it's not that you can just simply attack this computer uh, or the cloud, but you can also attack the network which is connecting these two together. So vulnerabilities are numerous in these systems, and sometimes they are outside of the control of one single company or entity. So that's where the side channel attacks also become important. So just to visualize it from mechanical engineers perspective, that can this be a problem in 3D printing, that security be compromised? So this is not the most latest taxonomy out there. There's a lot of literature on the taxonomies now, but this one is easy to interpret just because you can make connections very easily. That why would somebody do it? When will they do it? How will they do it? What would be the outcome of that? So this one example is given here, which says that maybe it is a CAD software, it may be a cloud software, or it can be the connection compromised by some sort. And the attacker can do the design mutations. Design mutation can reduce the strength. So this is similar to drowned attack that Mark had shown, that reduced strength can cause failure. Why would it happen? Maybe criminal intent, or somebody wants to inflict financial damage. And where could it happen? It could happen in file storage when you finished your day's work and you went to sleep, and somebody else came into the system and conducted this attack. So you have to make these connections for your specific supply chain and the product and come up with scenarios where there could be a problem. So, so this kind of analysis is extremely important, and you can create heat maps for your products and see how they work. So analyzing all these supply chains in additive manufacturing and different kinds of industrial scenario, including large companies producing their own parts, SMEs are producing parts for large companies. There are contract manufacturers simply providing designs to large companies. One example can be, NASA is asking contractors to design certain parts, and then there is a printer at the International Space Station up there where astronauts will print the parts directly. So in that case, what really is the product of this small company? The product is not a physical object, but it's just a design that they are transmitting. And then there is a process in place to print the design on the Earth numerous times and see what kind of properties and defects are there. Eventually find some sort of confidence in their design and transmit it to the International Space Station, where they'll print one or two pieces, test, and then deploy it. So that's a new type of supply chain that has come up in this area. But when you look at it very carefully, most of these attacks can be classified into four classes. And it could be side channel attacks, or direct sabotage, reverse engineering, or counterfeit production. So what Mark talked about, I would classify most of it into the side channel or the direct sabotage type of attacks. more into the computer science realm where people can compromise your systems or compromise the other systems which are connected and then cause the damage. But then in the cyber physical system that we are dealing with in manufacturing, the bigger possibility here is that you have a component that you print, you sell it to somebody, somebody buys this legally, and then they go and do the reverse engineering. They just create the replicas of that. They can do the CAD modeling. They have all the measurements. They can conduct even mechanical properties, and then they can create the replica. So how do we deal with these kinds of reverse engineering scenarios? Or how do we deal with counterfeit production scenario where either the files are stolen or recreated and then 3D printed on high quality printers? So sometimes the quality of the part is not a problem because many job shops have state of the art systems where you can take your designs and or maybe just email them and they'll ship it back to you. But this problem very specific to hardware sector, I think we have to contribute to security to these scenarios and not just rely on computer scientists. So in our group, we took this approach. We said that how do we set up these secure CAD models? So if somebody steals my CAD model, still they are not able to print the part in high quality. There need to be some sort of security features. Now you can do password protection of files, you can do encryption of files, all that can be done on top. But as a designer, can you set it up? And I'll give you a ridiculous example like on the screen, a gear looks like it has 32 teeth, but when you print it, it prints with 16 teeth. Or a gear that has the circular shaft hole in the middle, but when you print it, it prints with a square hole in there. And you'll see examples of this work that these things can be done. And there are lots of features in CAD program that we had never exploited before, but now we have need to do that. We're also looking into embedded authentication codes because we can hide the information when we are printing layer by layer. We don't have to stamp a product ID number or serial number outside, but that can go inside. And it can be encrypted, it can be again obfuscated into something that's hard to read. And finally, we can look into the encryption and cryptography from our perspective, like obfuscation of designs themselves. So I won't talk about encryption and cryptography today, but I'll give you examples of other things. So here what's happening in CAD model is that, we've been using it for years. Like I've been using CAD for more than 20 years now. But here what the problem really is that now the CAD file itself is becoming an input for 3D printer in this process. So whatever feature you see in the CAD file, and this is one thing that we see very often that when you convert it to STL, now you have a faceted design for a hole. Is something that was completely circular now is faceted design. And anything that had curvature here, now you can see that these are steps here. And 3D printers are actually interpreting these designs as steps. They are not interpreting them as a circle most of the time. Now, algorithms are coming up to deal with these things directly, but you can imagine that laser toolpath is still going to fill the space in between. And there's going to be some places, especially in FDM or material deposition type printers, where this is going to be a problem in some time to come. And the quality is compromised based on some of these features that you see here. So what can we do about these things? We started looking in this problem even more, that suppose you create a spline, and that's the example that we'll take further, that this used to be just a straight bar. We created a spline in there, and then we started tracking what happened to this spline as it goes through the process here. So what we figured out was one thing, that printing orientation makes a big difference in these FDM printers, because if the resolution on the XY is not the same as the resolution on the YXZ plane. And that's the reason that some of these features, if you design them to be of the correct size and correct shape, then you can get a lot out of these methods here. So here you can see that for the XY printer, there is this part which showed up here at certain resolution, not all the resolution, but only on the coarse resolution STL conversion. And when we convert this into an XZ orientation, in that case, there is a very different set of features that you can see lots of discontinuity show up here in the same part. And this is very different compared to what we had seen in the XY orientation. So how do we use it for our benefit? Does it translate into the printed part? So yes, the simple answer is that what you see in the sliced part is most likely what you are going to see in the final printed part. You can still fine tune it based on the mismatch between printer resolution and the slicing resolution. But if you are unsuspecting person working with a standard flow, then you are going to end up with these kinds of discontinuities in your product. And these discontinuities, when you do the tensile testing, you'll see that this spline is going to see a failure right at the tip due to the stress concentration, which is what happened in the tensile testing here. Now, the point here is to exploit this further and try to use it for the security purposes. So I gave this exercise to my students and I said, design a product that when I see on the screen looks like a perfect product, but they should print different in X, Y, and XZ orientation. So they took up this challenge. And here you can see that there is a set of these defects right here, all the holes here. So if this part was supposed to be in some sort of environment with lubricant or some gases or something, this is going to leak for sure pretty quickly with all these defects. This is not going to last very long. And on the other side, what you can see is that this is the square shaft tray and the circular hole. But now the printing direction is completely reversed. So you have the material deposited where it was supposed to be a hole, and the material is not deposited in the square shaft hole. But these are printed from the same files, just in different directions. So they were successful in demonstrating that features can be hidden in plain sight, and the printing orientation would be a big deal in finding that out. So if you don't know what this part is supposed to be like, you might be just printing with a square shaft hole and then reverse engineering your shaft accordingly with a square hub or something like that, that takes you in a wrong direction. But then you can think of other strategies based on the same things. And I'll come up with the Hack 3D on my last slide, just to pitch that event again. But this is a hackathon that we had started where we hide these kinds of features in CAD models and ask participants to decode them. On the front of the embedded identification codes, um, again, the inspiration was this figure that we can hide something in the layers here, and then we can do a CT scan or ultrasonic imaging, radiography, or something, and all kinds of non-destructive evaluation we are already conducting. So this kinds of information can be visible when we do the same non-destructive testing. And you can imagine that if the size of this code is very small compared to the size of a part, then it's not going to have impact on the mechanical properties, which is what we have also studied. And these codes can be miniaturized. They can be almost 100 microns by 100 microns or even smaller, depending upon the printing resolution that you have. So in our case, we started with this QR code because everybody knows a QR code these days. Doesn't have to be a QR code. It can be barcode, or it can be a serial number. It can be your own picture or whatever. Anything can be printed and hidden there. And we were able to capture this signature from CT scan. And this work is quite intensive in terms of image processing, because this printing is never perfect and the image capturing is never perfect, and eventually you end up with a CT scan QR code which is imperfect, but you can read it by image processing. So we have published that part yet. What was more exciting was that possibility of breaking this QR code into hundreds of parts and obfuscating it. So what happens in this case is, if you look at a particular direction, maybe this direction, it's going to look like the QR code, which is here. But any other direction will only show you a cloud of points, which is like this. So now you have to rotate this part numerous times just to see which direction would make the real QR code. And sometimes it's extremely difficult to actually capture that exact direction from which you will create uh, the QR code that can be scanned. Tensile properties were not compromised below certain level of this QR code size. But if it is large, then of course there will be an impact. What we also tried to do did quite elaborate studies on this QR code to see what we can do with it. So one important thing is that if you combine it with slicing, you can have both possibilities, that either you can keep this QR code in the sliced part, or you can completely eliminate all these little parts out there. So your final part will print with no QR code at all. So if somebody steals the file and they feel that, oh, this is something important to keep inside, they might end up by keeping hundreds of defects in their parts willingly, while your actual part which was printed has no code inside. So you have to figure out, these are all security methods that you would have to figure out for your own product and the type of scheme that you have. Here there are two QR codes which are segmented, and then they are inserted with each other, and finally these codes are either printed or not printed. So the final example here is the reverse engineering, which is emerging as a bigger issue right now. And example I took from composite materials, because we use a lot of intellectual property in creation of these composite materials, part with volume fraction and volume fraction, orientation of parts, and 3D printing direction, which is layering these things in different directions. But eventually what happens is that we can do the CT scan of these parts, do the image processing, run the neural networks, and just capture the entire toolpath using these machine learning method. So machine learning method was used to design this part, and now machine learning method is used to also reverse engineer these parts. And it's not very difficult process actually. Uh, so this shows that you can segment these images into smaller parts, and you can capture a lot of information from these machine learning methods. Uh, Very standard method. We did not invent a new method, but just applied the existing method. And we figured out that it's possible. So I don't have an answer to you yet that what could be an unclonable toolpath for machine learning methods, but maybe that's something that we have to look at. And I think this ties very well with the example Mark showed from Professor Panchal's work about the microstructure tagging and identification from there. So this slide just shows that these learned parts, reverse engineered parts, were very close in dimension to the original parts, and this could be a danger in future. So my last slide is here. My website here contains a lot of these resources that we have created. We had a webinar series of 4 webinars on AM security. If you didn't get a chance to capture it live, then we uploaded that on YouTube. Mark was on one of the panels, and 4 of these panels are now available. The course syllabus for the additive manufacturing security course we are offering, that's available there. And Hack 3D is a competition. So I'll take a minute about this Hack 3D competition. So Mark also mentioned about this approach of breaking these by teams, the encryptions. And this is the problem we gave this year in Hack 3D competition. A design of a light bulb, there was a filament with some type of obfuscated code, and participants had to break this code. We had 42 teams from around the world. 4 finalist teams were selected, and uh, this year NYU team won, but in previous years NYU team was not that fortunate to win. This was our 3rd year to organize this competition. So what happens in this case in cybersecurity is that a lot of these things are simply puzzle solving skills. You see some code and you have to make sense of it, like the obfuscated QR code that I showed you. If you want to write a machine learning algorithm or some type of algorithm to make sense of these 300 pieces, it's going to be a nightmare. You really need a high performance computer to try to solve all the iterations. But many humans would take this code and they will just rotate it around, and within few minutes they'll find this QR code. So if I have to do the probability analysis of finding the QR code, there's only one correct answer. But imagine that you can rotate this along any axis. You can rotate it along any axis at 1 degree, 2 degree, 3 degree orientations, whatever. Trillions and trillions of combinations which are possible to check, but only one correct answer. So the probability analysis is not giving us the real possibility of strength of this encryption or obfuscation. So these hackathons are really important for that purpose, that we have this human component for solving these problems. But unfortunately, it's hard to publish these papers because journals still ask for probability analysis, which now I know does not make sense. And we have a paper rejected twice from two different journals. That's basically reporting what we learned from this hackathon and Hack 3D. So I invite you to participate in these in the next offering, and I'll stop here now. Thank you once again for giving me this opportunity, and I'm happy to answer questions.
Thank you so much, Professor Gupta. This was a wonderful talk. A lot of interesting ideas here. I know that there is a text discussion going on in the chat window. So I would like to invite Adam to quickly summarize his three questions, and then I would like to invite Mark to quickly summarize his three answers, and then Josh to add on to that. So please unmute yourself and Adam, go ahead, please.
Am I unmuted? Okay,
Yes.
I think so. Okay, thanks. Well, thank you to both the presenters. This has been really fantastic. Just to sort of summarize some of the questions from myself and Kareem, who I'm working with here at Purdue. Our first question was more on how to combine sort of the three branches that Professor Yampolsky discussed. So specifically the legal and economic aspects of cyber security manufacturing with the attack and defense method research. So how we could engage policymakers as we work on addressing those aspects as engineers doing research on the attack and defense side. The second was more about
maybe maybe
go
we'll
ahead.
do question by
Yeah,
question.
that's fine.
Because
Sorry,
it will be easier. I'm sorry.
Sounds good.
Okay, I'm not sure how to engage the policymakers. Okay, with exception maybe that policymakers are interested in keeping jobs on, keeping security of manufacturing sector, but also that they need to understand the amount of investment that the manufacturing companies are putting into security, and also maybe organizations like NSF that are investing in security research in additive or direct digital manufacturing. It really depends on the assessment of liability in the case of successful attacks. Who is liable? Who is paying for successful breaches? Right now, it is Wild West. Nobody knows. So,
May I add something to that? I think it's a very interesting question, but I want to bring one more keyword here. I think policy and legal is important, but the bigger issue that I see really is the ethical issue. And I'll tell you why, because you can design a product with these security features, and at the end, if the security features result in a defective component, which are not visible to human eye or something, you deploy that component in somebody's car. Somebody, a third party manufacturer, just steals your design and puts in somebody's car. It's really putting somebody's life in danger. So this was not the issue when computer hacking was really the question. Nobody was going to die there if you hack somebody's computer or burn a computer chip or steal credit card data. But now these parts in aircraft, in spacecraft, in cars, in other places, and ethically, I don't think that's a good idea to have a security like that. We show the possibilities, but I think this is a bigger ethical discussion that we have to take, that how far we can go with implementation of security or mischief that can put somebody's life in danger. And on the policy side, I think there are lots of examples, but I'll give you an example that captures imagination very quickly. So for 3D printed guns, everybody, it gets charged up that, if gun designs are online, people will just download and print and kill. You still need a lot of infrastructure and knowledge before you start downloading gun blueprints and finding a shop to print and all that. I think you can legally buy much more easily. That's one part. But then, to me, the bigger point here is that suppose somebody downloads a design with the intention of printing the gun legally, okay? They purchases that from some online vendor. How do you know that this design was not compromised during this transaction? How do you know that this gun is not going to jam or explode or something, putting your own life in danger? So that trust is not there in this transaction yet. So this debate needs to be flipped from people doing wrong things to people actually doing everything right and still having this security issue come up. So that's the part I want to bring to the focus here.
I would say that this is very interesting perspective I have not considered before, and I think it is excellent. But this also brings another idea that this would also restrict the approaches like the ones that Dr. Gupta has proposed to certain products. Like if you want to prevent nuclear proliferation, right? We can integrate this kind of kill switch in designs for parts for nuclear fuel cycle that are 3D printed.
Yeah. So that's another perfect example that you want to stop nuclear proliferation, but do you want somebody who steals these designs to have a nuclear blast in a different country? So that's really the debate here.
Great point. Adam, do you want to ask your next question?
Sure. Thank you for that response.
Yeah.
So the next one is just more a question about, as we advance in sort of in situ metrology and additive manufacturing, if we lack security measures for today, but those metrology methods could be used to, say, steal some IP or otherwise compromise the system, like Professor Yampolsky discussed. How can we balance the trade-off between implementing that quality control and possibly losing IP? And I think this is where a lot of the side conversation has been happening. So thank you for that.
Yeah, and okay, my answer was that, okay, basically, if you are doing outsourcing or 3D printing or additive manufacturing, you technically cannot control IP theft. Okay, so there are methods, and side channel is just one of them. You can also hack computer. You can hack 3D printer. If you are managed end, if you are considering managed end attack, you are pretty much lost. At the same time, we need to think about the situation is similar to digital right management, what we had with DVDs or video files, music files. Now we have Netflix, right? Or Spotify. So there are different models that make unattractive to steal digital content, right? We need to figure out what are these digital models in the case of additive manufacturing, so that it is cheaper to go to a shop and outsource than try to do it itself, and it will not make sense for this shop to steal the design. Josh has contributed to this.
So there's one thing I can add to that answer if there's a couple of minutes available.
Please,
so
yes.
So one thing, I just made up this thing really recently because I'm thinking a lot about this whole testing issue that you print something and then you test and you get mechanical property data in there. But now if I'm championing a new scheme where we have design including a constraint of security as well, how's my testing going to look like? So in medical sector, people have taken this approach that no matter how you manufacture, if your properties are still the same as what you would expect from traditionally manufactured, the FDA would pretty much clear the part. So we could take the similar approach, but I think in short term, this is fine. In long term, we need a different strategy. So my proposal is this, that the testing that we do right now, it needs to evolve into trusting. This trusting means you trust either the part, you trust the process, you trust the parties, and you trust everything which is involved. Mechanical properties to the part provenance or anything. And that's what we need for the future of additive manufacturing, because that includes the communication system, it includes the software systems. And unless we get to the trust, this whole industry 4.0 is not going to be implemented here, because you don't know where the problem is going to come from. The machines have to talk to other machines in different companies. SME machines have to talk to main systems in parent company in a different city, in a different countries and all that. So this testing, I don't think is going to be insufficient in time to come.
Thank you. Thank you so much. I know Josh has an interesting perspective from a risk management perspective. Josh, would you like to add a little bit to this discussion? I know will have a complete talk from you next time.
Well, I don't have too much to add beyond what Mark and Dr. Gupta have already said, but um, I think it's really interesting to look at different sectors, and I think the risk landscape is very different. Say, if you're doing business with the U.S. federal government versus if you're producing a consumer product that's lightly regulated. So I guess I was just trying to make the point that it's one thing to do experimental work demonstrating the feasibility of a particular attack, but then you have to look at it in a larger context. Is anybody actually going to want to do that attack? What are the incentives? Do the incentives apply for this particular industry that you're focused on?
Yeah, absolutely correct. And this semester, the class I'm teaching, the additive manufacturing security, I gave students 5 case studies. And case studies were just pictures of parts and described what that part was, like an aircraft bracket.
Mm-hmm.
Made groups of students and asked them to create heat maps. So who will do it and why would they do it? Those kinds of things. I think I posted on LinkedIn a couple of these things. And every student had a very different perspective of risk for the same part. So then I created groups of 3 students and said, come up with consensus among 3 of you and see how your risk graph changes. And then I said the whole class has to come together and create a unified map. And then I said, go back and now see what you initially thought and what you converged at. And this is what happens in companies, that there will be risk analysis, and according to which there will be resources deployed in the security side. And as Mark said, a lot of times companies don't have the resources. So a couple of months back, I actually presented to a group of insurance companies because they wanted to understand how they should structure their insurance based on the risks which they perceive. And it's same as our house security. You know, we have locks and we have cameras, but we still purchase an insurance against theft and all that. And that landscape is going to survive, I think, this wave also.
This is great. I think we have 3 or 4 more minutes. Are there any other questions from anyone in the audience? Um, so I wanted to mention 2 things. One is, we want to make this a monthly webinar, and we have the date for the next month finalized already. It's December 18th, and Josh from NIST is one of the speakers, and we are still talking to a couple of other speakers to finalize the second speaker. And if you have any suggestions on other people that we should bring in onto this webinar series, please email Jan or myself. So that's the first thing. And the second thing is, Dr. Gupta, I really like this idea of Hack 3D. In fact, the CIE division, we have started organizing a hackathon as part of the ASME CIE conference in August. And we are looking for interesting new problems to add to our hackathon. So we'd love to continue this discussion with you to see if one of the problems can be from your group.
Definitely, and we have learned our lessons actually. I mean, we spend a lot of time creating complex problems, and we figured out if this is like a video game, if nobody can solve it, they would not even be motivated to solve it.
Yeah.
So you gotta give them something they can actually solve, and you can grade them based on how quickly they arrive at solution, what approach they take. But you gotta make sure the problem can be solved by people who are not really into security yet. Yeah, but I'm happy to collaborate. I have this Secure and Trustworthy Computing grant from NSF from education program. So we intend to continue this work, and we are constantly creating new problems in this area.
Great, wonderful. So yeah, Jan, would you like to add anything?
Yeah, so this is great talks, and yeah, thank you, Professor Jampowski and Professor Gupta. Definitely, there's an opportunity for us to come together from computer science and mechanical engineering. And of course, through the discussion and Dr. Ruba also mentioned, there's a risk issue here. So risk, of course, so this problem is so complex, going beyond non-engineering or computer science. Now you go to social science, risk perception, and I go to the insurance. Anything there's a risk, there's an insurance opportunity of business. So this problem becomes so bigger than we originally thought. So that's a great discussions we had. And we look forward to continue our discussion in following series of seminars.
Yeah, I would like to educate myself more on the ethical aspects of these things. So if you can develop some programming at some point, because as engineers, we are too formula driven, we are not into ethics analysis as such. I know ASME does a lot of work. They have a community on ethics, and I think that could be a good place to have some learning.
Mhm. Wonderful. Well, thank you all so much for attending. This was very informative. I look forward to the next set of seminars and this series.
Thank you very much for the invitation. It was very interesting.
Thank you very much.
Bye. Have a great day.
Yeah, thank you for attending, for the audience and questions as well.